Hey everybody, it's Tuesday, February 23rd, and as you can see here in the aim today, our goal for today's video is all about applying concepts associated with conservation of momentum to solve problems. And we're going to do that by making use of two worksheets that were attached to the post for today. I'd like you to go ahead and open the first worksheet now because we're going to just jump into this by taking a look at the first problem on the first worksheet. The first worksheet is titled Conservation of Momentum Collisions, Problem Solving Worksheet 3.0. And we're going to start by taking a look at the first problem here. Now, lately, when I've been giving you worksheets to do as a class activity, I've been telling you to do the worksheet entirely on your own, submit it, and then the solution video comes out the next day. But this video is going to be a sort of, interactive experience, if you will, where I'm going to ask you to pause the video a bunch of times, try the problems on your own, and then when you hit play, we'll go over the answers here, just so we can sort of move through this entire sheet in one day instead of spending 2 days on it. And so this first problem here, B5 SCT26, is the first problem I want you to work on. It's called Colliding Carts That Stick Together, Final Kinetic Energy. And it says here, two identical carts traveling in opposite directions are shown just before they collide. The carts carry different loads and are initially traveling at different speeds. The carts stick together after the collision. And you can see here the mass of the carts and the velocity of the carts. And it says here, three physics students discussing this situation make the following contentions. Alex says these carts will both be at rest after the collision since the initial momentum of the system is zero and the final momentum has to be zero also. Belinda says if that were true, it would mean that they would have zero kinetic energy after the collision, and that would violate conservation of energy. Since the right-hand cart has more kinetic energy, the combined carts will be moving slowly to the left after the collision. Chano, I guess, says, I think that after the collision, the pairs of carts will be traveling left at 20 centimeters per second. That way, conservation of momentum and conservation of energy are both satisfied. So obviously, you can see here there's broad disagreement amongst these three students. Your goal for this question is to answer with which, if any of these students do you agree, then that could be Alex, Belinda, Chano, or none of them, and then explain your reasoning. So I'd like you to take a couple minutes, pause this video here, go through these three arguments and evaluate which one of them you think might be correct. And once you've explained your reasoning, I'd like you to hit play and we'll go over it. Okay, so looking at these three arguments, we can definitely say they all sound fairly compelling, but there are key errors in two of them that ultimately make them wrong. And so I guess first we'll just go over the correct answer and then we'll circle back and talk about why the wrong answers are wrong. One of the students is correct. That student is Alex. Alex is correct. Alex said these carts will both be at rest after the collision since the initial momentum of the system is zero and the final momentum has to be zero also. And so we can say here, since there is no external net force acting on the system, the total momentum of the system is conserved, meaning the momentum before the collision is equal to the momentum after the collision. That's really just what conservation of momentum means. Notice that first sentence at least is kind of redundant. You don't need to say both of those things at the same time. If you just say the momentum is conserved, by the time we take the test, I'm going to understand you should know that means the initial equals the final. Then I went on to say, since the objects have the same magnitude of momentum, then I wrote here P equals mv, they have the same product of their mass and velocity, and so they have the same momentum. Since the objects have the same magnitude of momentum before the collision, but in the opposite directions, initially the object's momenta cancel, resulting in a zero final momentum. And so we can also say then, just to address what Belinda and Chano said, because they started to bring up energy in their explanations, that since the carts stick together, this is a perfectly inelastic collision. And this means conservation of kinetic energy is not a requirement here. And so when Belinda went on to say, if that were true, that would mean the kinetic energy after the collision would be zero, and that violates conservation of energy, that's wrong. First of all, conservation of energy is never violated. The kinetic energy that the carts lose is turned into heat. What a perfectly elastic collision requires is conservation of kinetic energy. But since this isn't a perfectly elastic collision, rather it's a perfectly inelastic collision, conservation of kinetic energy isn't required. And that ultimately is why that answer is wrong. Take a second to pause this video here and write that down, adding any parts to your explanation that may have been missing. And when you hit play, we'll move on. So just to circle back here, as we mentioned, Belinda and Chano are wrong. And just to be clear, you want to really make sure you're being careful when you're looking at the situation that you are identifying the type of collision. The way you should have been able to tell Belinda and Chano were immediately wrong is that they're talking about conservation of kinetic energy or conservation of energy, and conservation of kinetic energy is not required for this problem. Conservation of energy is true and valid here in general, but it doesn't necessarily tell you anything about the motions of the carts because conservation of kinetic energy just doesn't apply to this situation. Now, something else that we should also mention, because it comes up again and again and again in AP Physics problems, it's like a very important canard for you to be able to identify, is Belinda is talking about the right-hand cart having more kinetic energy. And so that means because that cart on the right is moving to the left, the fact that there's more, quote, energy toward the left means the cart should be moving to the left. That is dead wrong, and that's something you need to be able to identify. Huge note. This is something you really should be writing in your notes. Kinetic energy can never be used to determine the direction of any object or objects after a collision because energy is a scalar. Momentum, the vector, is the only relevant quantity that determines the direction of the final velocity. That is extremely, extremely important. Take a second to pause this video here and write that down. And when you hit play, we'll move on to the next problem. The next question is actually two questions that refer to the same situation. We'll take a look at the first one here. You'll see this on the worksheet if you scroll down to the back. It says here, the following two questions refer to the diagram below, and you can see here we've got a graph of velocity versus time that looks kind of odd, different from anything you've seen up to this point. It says here, block 1 of mass m1 and block 2 of mass m2 are sliding along the same line on a horizontal frictionless surface when they collide at time t sub c. Now notice the subscript c there means collision. And it says the graph above shows the velocities of the blocks as a function of time. And it says which block has the greater mass and what information indicates this. This is a classic example of a kind of question they'd ask on the AP test because they like to include the answer and the correct explanation in the multiple choice answer choice description, so they really make sure you understand this. So the choices are A, block 1, because it had a greater speed before the collision, B, block 1, because the velocity after the collision is in the same direction as its velocity before the collision, C, block 2, because it had a smaller speed before the collision, and D, block 2, because the final velocity is closer to the initial velocity of block 2 than it is to the initial velocity of block 1. What I'd like you to do here is take a couple of minutes to evaluate each of the answer choices, thinking about why they may be right or wrong. And as you can see on the worksheet, or as you should be able to see on the worksheet if you have it open, there's a box next to this that says explain. Now, as I mentioned, the answer choice already does have a little bit of an explanation in it. But what I'd like you to do is just really sort of address that in a little bit of greater detail in the explanation box, because essentially I'll give you a little bit of a hint here. The reason why the thing in the answer choice is true is what you should be writing down. So to be clear, what the answer choice says is the answer and a reason why it could be considered true. What I want you to write in the explanation box is the reason why that additional piece of information in the answer choice is true. So take a couple minutes to pause this video here and work on this question. And when you hit play, we'll go over it. Okay, so the answer here to this question is choice D. The answer says block 2 because the final velocity is closer to the initial velocity of block 2 than it is to the initial velocity of block 1. That's the reason. The reason why it's block 2 is because the final velocity is closer to the initial velocity of block 2 than the initial velocity of block 1. What I hope you wrote in your explanation is the reason why that makes sense. And so what I wrote here is the blocks both have the same final velocity, which tells us that this collision is a perfectly inelastic collision. In other words, these blocks stuck together. When blocks stick together, they have the same final velocity. So the way that you can tell that the blocks stuck together is because they have the same final velocity. So in a perfectly inelastic collision, the final velocity of the system of blocks is always closest to the initial velocity of the objects with a larger mass. Since the final velocity is closest to the initial velocity of block 2 has a larger mass. Now, of course, the big question here is, why is that true? How do we know that that's true? How do we know that when an object experiences one of these collisions, that the final velocity is going to be closer to the initial velocity of the object with the larger mass? Well, it all comes down to momentum conservation. Momentum is conserved because of Newton's third law, so we can say here this is true because the fact that the objects experience equal and opposite forces means the objects experience equal and opposite impulses. And since impulse is the product of the mass and the change in velocity, J equals m delta v, the object with the larger mass should have the smaller change in velocity. Because when you take the mass times the delta v, it's got to be the same number. So a bigger mass is going to give you a smaller delta v. Smaller mass is going to give you a bigger delta v. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Moving on to the next question, the second part of this two-part series of questions about that graph. It says here, how does the kinetic energy of the two-block system after the collision compare with its kinetic energy before the collision, and why? It says here, choice A, it is less because the blocks have the same velocity after the collisions. Some of their kinetic energy was transformed into internal energy. B, it is less because the blocks have velocities in opposite directions before the collision, so some of their kinetic energy cancels. C, it is the same because the collision was instantaneous, so the effect of external forces during the collision is negligible. And D, it is the same because the blocks have the same velocity after the collision and there is no friction acting on them. Take a second to pause this video here and try to come up with an answer. And I want you to think about a reasonable explanation supporting the information that is posed in the answer choice. As was the case for the last problem, as you can see on the worksheet, there's a little explain box next to this question as well. And so I'd like you to take a stab at an explanation. When you hit play, we'll go over it. Okay. The answer here to this last question is choice A. And as far as an explanation is concerned, again, choice A says it is less because the blocks have the same velocity after the collision, so some of their kinetic energy was transformed into internal energy. We can say, since we can see the objects have the same final velocity, we know the collision must be a perfectly inelastic collision. We already addressed that in the explanation to the previous part. Since the collision is perfectly inelastic, we know the kinetic energy is not conserved. So the final kinetic energy will be less than the initial kinetic energy. That's like the key defining characteristic of a perfectly inelastic collision. And so what I wrote here is some of the initial kinetic energy was transformed into internal energy, or heat, due to the frictional contact between the blocks that enabled them to stick together, making the answer choice A. Now, let's be clear about one thing. If you go back to the initial description of the problem does say the blocks are rolling or sliding on a frictionless surface. But that doesn't mean when the blocks crash into each other, there is no friction. The fact that the objects crash into each other, rub on each other, and stick together tells you that it took some energy to do that. And that's why the kinetic energy is not conserved. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, and just very quickly before we move on to the next worksheet here, I just want to go back and look at some of the wrong answers here in this answer choice. Notice none of the answer choices say the final kinetic energy is more, and so that's good at least, because that would really make no sense. That would be a true violation of conservation of energy. The answer choices that say it's the same are just wrong. And the reason why they're not the same, again, is because whenever the objects stick together, it takes kinetic energy to do that. And so the objects lose, or I should say in general, it takes energy to do that. And the only energy that's there in the beginning is kinetic energy. And so some of that kinetic energy has to be used to make the things stick together. Additionally, as far as the two answer choices that say it's less are concerned, choice A is the best one because notice B is giving that classic AP physics distractor, talking about kinetic energy having a direction. Choice B says it is less because the blocks have velocities in opposite directions before the collision, so some of their kinetic energy cancels. Kinetic energy can't cancel. It seems to make sense. One has energy going to the right, one has energy going to the left, so the energy cancels. It's not how energy works because energy is a scalar. Energy cannot cancel because it is a scalar. It can only add. That's a very important thing to realize. Let's move on to the second sheet. If you take a look here at the second sheet attached to this post is entitled AP Physics Conservation of Momentum Qualitative Reasoning. And there are a couple of questions here which I'd like you to take a look at before we wrap it up for today. The first one is one of these Tipper's book questions, B5 WWT 20, two skaters pushing off each other, force. And it says two skaters, a large girl and a small boy, are initially standing face to face, but then push off each other. After they are no longer touching, the boy has more kinetic energy than the girl. A physics student who is watching makes the following contention about the forces the boy and the girl exerted on each other. They say, since the boy has more kinetic energy, he also has more momentum. So the girl had to have pushed harder on him than he pushed on her. Your task is to answer the question, what, if anything, is wrong with this contention? If something is wrong, identify all problems and explain how to correct them. If this contention is correct, explain why. Take a couple minutes to pause this video here and answer this question, and when you hit play, we'll go over it. So I think when you're looking at this question, the first thing that you should do is evaluate all of the initial information given to you and see if that's right. Because notice the person who's making this contention says, since the boy has more kinetic energy. Well, is that true? Well, it does make sense here that since it says a large girl and a small boy, that because the boy has less mass here, we would expect the boy to end up going faster. And the fact that kinetic energy is 1/2 mv squared, it should make sense that the boy does have more kinetic energy. So at least that part makes sense. But if we look at the rest of the claim that the kid makes here, it doesn't add up. And so the answer here is that no, of course the forces are not different. They're equal. Why are the forces equal? Well, the first thing that we should say is we got to attack the reasoning that this kid gave. And the reasoning that this kid gave said, since the boy has more kinetic energy, he also has more momentum. That's wrong. The fact that the boy has more kinetic energy does not mean he has more momentum. As you can see, we derived the equation when we were first talking about momentum that said the kinetic energy in terms of the momentum can be written as p squared over 2m. Notice if you take p and you square it, you get m squared v squared. And if you divide it by 2m, you get 1/2 mv squared. So if we take the square root of 2 times the mass times the kinetic energy, well, then we get mv, and that's the momentum. And what you'll see here, since we can write momentum as the square root of 2 times the mass times the kinetic energy, is the fact that the boy has more kinetic energy does not mean he has more momentum. Because the reason the boy has more kinetic energy is because they have less mass. And so the idea is, yes, it is true that the momentum is directly proportional to the square root of the kinetic energy, but it's also directly proportional to the square root of the mass. And the kinetic energy is only bigger because the velocity of the boy is bigger, because the fact that kinetic energy is 1/2 mv squared means the velocity really matters in terms of determining the size of the kinetic energy. So that's at least the first thing we should say. The fact that the boy has more kinetic energy does not mean he has more momentum. Actually, we should know by now the boy and the girl are going to end up having the same momentum because momentum is conserved. And so what we can say here is that since there is no net external force or no external net force exerted on the boy-girl system, the total system momentum is conserved. Since they both start at rest, the initial momentum of the system is equal to 0, which means the final momentum of the system is also going to be equal to 0. In order for the final momentum of the system to be 0, the momentum of the boy and girl must be equal and opposite so that they can cancel. Notice, energy cannot cancel, but momentum can. And that's because momentum is a vector. I went on to write, since the impulse, or change in momentum, must be equal and opposite, and the time interval over which the force is applied must be equal, then the forces must also be equal and opposite, which is in accordance to Newton's third law. Now, this is a little weird because we usually argue this the other way around, but it's got the right idea. J, impulse, in addition to being equal to m times delta v, is also equal to F net times t. And so we can sort of, in a backwards way, kind of argue that if the impulses are equal and opposite and the times are equal and opposite, the fact that the impulses and times are equal and opposite tells you the net force is equal and opposite. At the end of the day, Newton's third law applies always. The forces these objects exert on each other are equal and opposite. And since there is no net force, the fact that they both experience equal and opposite forces means they'll get equal and opposite impulses, which tells you they'll experience equal and opposite changes in momentum. Take a second to pause this video here and write this down, adding any parts of this explanation here that might be missing from your explanation. And when you hit play, we'll move on. Moving on here, the next question on this sheet, B5WWT22, is titled Ball Hitting a Wall Momentum. And this problem here says, a student observing a rubber ball hitting a wall and rebounding states, the change in momentum for the ball is equal and opposite to the change in momentum for the wall, because in the situation, momentum has to be conserved. What, if anything, is wrong with this statement? If something is wrong, identify it and explain how to correct it. And if this statement is correct, explain why. I'd like you to take a second to consider this situation here, come up with an answer and explanation, and once you have that written down, hit play, and we'll go over it. There's something important to realize about these conservation of momentum problems as you go through and look at the sort of weird situations that they're going to give you on the AP test. And the thing you need to realize is that you want to make sure you're being very careful about considering whether momentum is conserved or not. Because what I often see is that when you have this idea drilled into your head that like momentum is conserved, energy is conserved, momentum is conserved, energy is conserved, that you take it for granted and think that it always is conserved. And that's not the case. Momentum is only conserved in the absence of external forces. And while the ball experiences an external force from the wall, so we'll consider the wall as part of the system, the wall does not only experience an external force from the ball. The wall is connected to the rest of the building. And so as a result, momentum is not conserved here. In order for the momentum of a system to be conserved, there must be no net external force acting on the system. If the ball and the wall are to be considered part of the same system, when the ball collides with the wall, the floor and ceiling must exert a force on the wall to keep it stationary, because the idea of a wall is for it to not move, right? So the momentum is not conserved here. The change in momentum, impulse, for each object is only the same if the momentum is conserved. And since the momentum is not conserved here, the objects will not experience equal and opposite impulses. This is a very important thing to recognize. It's really important that you think of which objects you are going to consider to be part of the system, and then whether there are any external objects exerting forces on the objects you've now considered are part of your system. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll look at the final question for today. Last question for today is a two-parter, but this is a very important question because, like the direction of the kinetic energy thing, this is a kind of problem that comes up on the AP test again and again and again. It says here, this problem is called B5CT25, bullet strikes a wooden block and bullet speed after impact. In case A, a metal bullet penetrates a wooden block. In case B, a rubber bullet with the same initial speed and mass bounces off an identical wooden block. Now you can see, in case A, the bullet is moving to the right. It gets stuck in the block, and as you can see from these like motion lines here, the block and the bullet move to the right. And in case B, the rubber bullet bounces off the block, and now it's moving to the left, as you can see from these motion lines, while the block is moving to the right. And it says, will the speed of the wooden block after the collision be greater in case A, greater in case B, or the same in both cases? And explain your reasoning. I'd like you to take a couple minutes to pause this video here and think very carefully about the answer and the explanation to this problem. And when you hit play, we'll go over it. All right, now before we go over the answer here, I just want to say, often what people think is the correct answer to this question has something to do with the fact that these objects in their collisions with the blocks are representing the two main types of collisions. In other words, that case A, because the bullet penetrates the wooden block and sticks to it, represents a perfectly inelastic collision, where in case B, we see that it's a perfectly elastic collision. We don't necessarily know that that's true for case B. There could be some energy lost in that collision, making it just a regular old type of inelastic collision, meaning it's not perfectly inelastic, it's not perfectly elastic, it's just in between. But the basic idea here is there's a better answer and a better explanation for why the speed of the wooden block is greater in case B. And we can say here the speed of the block will be greater in case B. Since there is no external net force exerted on the bullet block system, the change in momentum of the bullet is going to be equal to the change in momentum of the block. If you remember from when I first introduced momentum, I really tried to stress that the fact that the impulses are equal and opposite is like a really, really important topic here. It's a really important piece of content for these kind of problems. And it's really important that you think about problems in that way. Because if you think about the fact that the impulses are equal and opposite here, then you'll realize that when the bullet rebounds, the change in momentum of the bullet is larger than when the bullet just slows down or stops. So the change in momentum of the block is larger, thus resulting in a larger speed for the block. It probably makes sense here to take a moment to explain this. And so I want to do that very quickly before you pause to write this down here. The equation for impulse is m delta v. And so we can expand that out by writing J equals m times v final minus v initial. And so that means you basically have two examples here, when it sticks or when it rebounds. Now, in both of these cases, the impulse is going to be negative because the force is acting in the opposite direction of the motion. And so it's going to be negative by default. But we can say here, let's say when it sticks, the final velocity of the bullet block system is like 10% of its initial velocity. So the final velocity is going to be 0.1 v naught. The initial velocity, of course, is going to be v naught. And so that means the impulse here is going to be 0.9 m v naught. Right? So even if the object slows down to 10% of its initial velocity, the impulse is going to be 0.9 mv naught. In other words, that's how much momentum it lost. It lost 90% of its speed, so it lost 90% of its momentum. And if the object rebounds, and let's say it rebounds even only to 0.1 of its initial velocity or 10% of its initial velocity, but in the other direction, so it bounces and goes back to the left now, the fact that that velocity turns negative means that when you just calculate the impulse, negative 0.1 v naught minus v naught is going to give you negative 1.1 m v naught. Notice, even if instead of the velocity being 0.1, if it just rebounds totally with the same initial velocity as it had in the beginning, you get negative v naught minus v naught equals negative 2 mv naught for the impulse. The point is, if you actually just look at the numbers, when an object rebounds, its change in momentum is bigger because it loses all the momentum it had in the original direction it was going in, and then gains momentum in the opposite direction. And that means the impulse is larger. And so whenever an object rebounds, it experiences a larger impulse. And the point here is because the impulse delivered to the bullet is larger, then that means the impulse delivered to the block is larger because the impulses are equal and opposite. Take a second to pause that video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, so before we move on to the second part, I want to write down a note because this is extremely important. It comes up on the AP test again and again and again. When momentum is conserved, the impulses delivered to each object are always equal and opposite. And since an object always experiences a larger change in momentum when it changes direction compared to when it slows down or stops, the change in momentum delivered to the object it's rebounding off of will always be larger when the object changes direction. They're always going to ask you to compare the impulse for an object that sticks compared to an object that bounces. And the idea is the impulse is always bigger when it bounces. Very important. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Moving on to the last question here. This is part B of that question, B5CT25. Part B now says, in case B, where the thing rebounds, will the speed of the bullet after the collision, after it's bounced and starts moving back in the opposite direction, be greater than, less than, or the same as the speed of the bullet just before the collision? Last question, I want you to think about it. Take a second to pause this video here and think about this question. And when you hit play, we'll go over it. Now, it's important to realize a lot of people get the impression that the way to answer this is by thinking about energy. But since we don't know what kind of collision this is, whether the kinetic energy is conserved or not, we are better off trying to address this using concepts of momentum. And so what we can say here is that whether we use concepts of momentum or energy, frankly, but I want you to think about momentum, the answer here would be the same, and that would be that the speed after it bounces off the block's got to be less than its initial speed. And what we can say here is since there's no external force exerted on the system, the total momentum of the system must be conserved. Since the momentum of the system initially must be equal to the final momentum, if the block has some non-zero final momentum, then the momentum of the bullet must be less than it was initially, which means the speed of the bullet must be less than it was initially. If the momentum is less, then the bullet must be less. In other words, the only thing with momentum in the beginning was the bullet. The bullet gave some of its momentum to the block. Since the block has some of that momentum, the bullet has to have less than it originally did, right? If the bullet had 10 momentums, if you will, and it gave one of them to the block, that means it only has 9 left over, right? That's the basic idea. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, everybody. With that, that's it for today. Hopefully you got something out of taking a look at these problems here and seeing how they can be applied to a wide variety of conceptual questions. And tomorrow, we are going to pick it back up by thinking about how these momentum concepts apply to some more experimentally focused situations. All right, everybody. Have a good one.